All right, so here we're going to take a look at proofs by contradiction. All right, so we have a proof by contradiction. We're going to go over two famous examples here, right, common examples to show this proof by contradiction. Right, so essentially the proof by contradiction is that you're given a statement P, right? And instead of proving P, you prove the statement not P. You negate the statement P. And the idea here is that you make, using a valid argument right here, you give statement using definitions, other theorems possibly, right? And then at the end, right, when you kind of evaluate it, what you arrive at is a contradiction, right? So at the end, so statement, all these are valid, right? And then at the end, you reach, here usually the notation here sometimes used for a contradiction is, you get something like this, right? A contradiction. For example, like 2 is equal to 3, right? Just something that is just wrong. And we assume that all these statements are valid. All your argument is great. There's nothing actually wrong with that, right? So then what that implies here is that, well, if all of the statements were used correctly, definitions, other theorems were used appropriately, and that led us to a contradiction, well, there's only one thing that could have been wrong, and that could have been our initial assumption. So our initial assumption is false. In other words, not P is not true. So if not P is true, that means that P must be true. Right? Because remember, what essentially is implying is that we want to prove this, right? P and not P, but that's impossible. Right? Something cannot be both in P and not in P. All right, so that's where we arrive at our contradiction. All right, so now let's take a look at here. Excuse me. And we want to look at, so we want to prove that the square root of 2 is irrational. And we're going to do this by contradiction. All right, so I'm going to prove okay, so the statement that I'm going to prove is that square root of 2 is rational. And I'm going to arrive at some kind of contradiction. Okay, so now we need a couple things beforehand, right? We use the set notation Z for integers. We're going to use the set notation Q for rationals, right? Now the Q is defined as the set of AB such that A and B are element of the integers, right? So that's very generally what a rational number is. It's a ratio of 2 integers. So if I assume that the square root of 2 is irrational, then I can choose an A and B, or there should exist, A and B, such that A over B is in lowest terms, and square root of 2 is equal to A over B. Okay, so I should be able to write it as a ratio of 2 integers in lowest terms. All right, so this should exist if the square root of 2 is rational. So we start from there, right? And we say, all right, well, this is where I begin, and I go about here, let's say, taking the square of both sides, so just doing some algebra. Here, multiply b squared by both sides, and we get a squared. Okay. Okay, so here we have that a squared is even, right? remember B and A are integers, is even, therefore A is even, right? All right. So we'll state this without proof. This is in fact a true statement. If A squared is even, then A is even. All right, so if A is even, then I can write A as 2K. Right, so if I do that, 2B squared is equal to 2A, or excuse me, 2K squared, which is 2B squared 4K squared. So that means that B squared is equal to 2K squared. And in general, I have that B squared is even, which means that B is even. But this cannot be possible, right? Our initial assumption stated that A over B must be in lowest terms. So if A and B is even, then they have a common factor of 2. But that goes against my initial assumptions, right? That there exists an AB in lowest terms such that root 2 is A over B. So we've arrived here at our contradiction. But every step along the way, right, was valid, right? I used proper definitions, I used them properly. So my contradiction is not in the way that I wrote the proof, but it's in my initial assumptions. So square root of 2 cannot be rational. In fact, square root of 2 is irrational. Okay, so that's again another approach for our proof writing, right? Showing that something is the negation of the statement. All right, let's go over one other proof here. Now this one is called, so this proof is the proof of something called the pigeonhole principle. So the pigeonhole principle says if more than n pigeons fly into n pigeonholes, then at least one pigeonhole will contain at least 2 pigeons. Okay. Now, first of all, again, what this statement tells me and doesn't tell me. So here what this is saying is, let's say we have, this represents our pigeons. And this represents our pigeonholes. Okay, so it says that if we have more pigeonholes, okay. Okay, so in this case, we have 4 pigeonholes and 5 pigeons. Okay, so what the pigeonhole statement says that I'm guaranteed that one of those holes will have more than 1 pigeon, sorry. In one of them, right? Again, not all of them, right? So one thing that it doesn't say is that it doesn't say that all of them will have a pigeon, right? So here what you focus on the absolute most extreme scenario, right? So we could say that, all right, we could start here, each one of them can go into a different pigeonhole, right? But when I get to the 5th one, right, there's no more holes left, right? So here I'm guaranteed that it has to go into one of those four holes, but one of those four holes also has a pigeon, so I'm guaranteed more than one. Right, now again here, this is not stating that each hole will have at least one pigeon. Right, because we could also have this, right? This does not violate the pigeonhole principle, right? If I read that, it says if more than n pigeons fly into n pigeonholes, then at least one pigeonhole will contain at least two pigeons. And we can see there one of them contains, in this case, all of them. All right, that is still in line with the pigeonhole principle. Okay, so make sure we understand kind of what that is telling me and what can I deduce from that. Okay, all right. So now in proving this, right, it's actually a very straightforward proof if we do the contradiction. Right, so the negation statement would be that each pigeonhole contains at most one pigeon. But right away, right, if this is our negation, we could say this just contradicts our initial statement, right? Because we have more than n pigeons and only n holes. So there's just not enough holes for my more than n pigeons. So right away we have arrived at a contradiction. So the pigeonhole principle is true. It must be a true statement, right? Another way to think of this, think of if you're in a group of people, right? And you're looking for shared birthday months. When are you guaranteed to have two people share the same birthday month? Right now, we could have just two people, right? The first two people, they might share the same birthday month, right? But that's not guaranteed, right? We could have three people, right? Again, right? Two of them might share a birthday month, but that is not going to be guaranteed, right? So I want to make sure that I have the right amount of people to guarantee me that someone shares, that a pair share a birthday month, right? Well, we take a look at, right, 12 months, right? And we can think of these as the holes, right? Now, how many people do I need to guarantee that at least 1 month two people share a birthday? Well, I need to have more pigeons than holes. So that means that 13 students, and then I'm guaranteed, right, that at least two share a birthday month. Now here, be careful what that is, the implication there is, right? I'm not saying that in those 13 people we're going to have one person for each month. Not at all. The only thing I'm able to guarantee is that a pair of students will share a birthday month with 13 people. Okay? That is it, right? That is all we're guaranteeing there, right? Maybe there's several pairs that share other months, right? That could still possible. Maybe they all have the same month. Also, still a valid deduction from the pigeonhole principle, all right? Or at least it doesn't go in the face of the pigeonhole principle. Okay, so just keep in mind here, when we are referring to the pigeonhole principle, right, it's a more abstract concept in terms of, think of holes as containers and the pigeons as objects, right? And ways that you can distribute these objects into n containers.